case, and we prove that this functor is a left adjoint, and in the end, I mentioned a theorem by Eilenberg and Moore. The functor preserves homotopy pullbacks very well. Now, what exactly does this phrase mean? Well, let's talk about that. I think it's I think it's useful. So I will only need two versions. We'll need this category and this category, but let's start by taking D to be an arbitrary small category. If we have another category C, we denote the category of functors from C to D as C to the D, which is how people often denote function things. We have the constant diagram functor from C to the D. Basically, to every object C, we associate sorry, it's supposed to be the other way around. D to the C. So to every object of C, and to every arrow we associate the identity arrow. Now, this functor, in all interesting cases, has both adjoints. In which case the left adjoint is called the co-limit of the diagram of a diagram of shape D, and likewise the right adjoint is the limit. So we we have C which goes to the C to the D. The right adjoint is lim, and the left adjoint is co-lim. Okay, now suppose C is a model category. Now, it often happens that neither limit nor co-limit preserve weak equivalences. Well, for example, let me take C topological spaces. And the D to be this diagram. It has three objects, two non-identity areas. Well, let's observe that we have this diagram, and it commutes. So what's the co-limit of the top row? So I have Sn, which maps to the point, and again to a different point. What's the co-limit? Yes. Is this clear to everyone? Okay. Now we can take disks instead of points. So let me take two disks and embed Sn in both of those as the boundary. What's the co-limit? Yes. And these spaces are not homotype equivalent. So if we want to have a homotype invariant definition of the co-limit or of the limit, we need to think. So the question is, how to make the limit, the co-limit, homotype invariant. Well, the answer is very simple. There is a model structure for co-limits. For limits, there will be a similar answer. Model structure on okay. Now here I take I want to take G equal the simplest interesting diagram, the one which defines push-outs. In which case there is a model structure on C to the D. Such that the weak equivalents are object-wise weak equivalences, and this pair of adjoint functors becomes equivalent junction. So we have C, colim C to the D, is equivalent junction. And then the homotype then there is a pair of adjoint functors between the homotypic categories. And the one which is obtained by deriving the co-limit is the homotypic co-limit. Does this make any sense? Yes, no, sort of. Now, perhaps perhaps it would help if I explain how to calculate the homotypic colimit. Suppose I have a diagram of this shape in C. Then it's possible to replace this diagram in the functor category by another one. Where the object in the middle is cofibrant and the arrows, both arrows, are cofibrations. And the homotypic colimit of the diagram is the same as the usual colimit of the replacement diagram. For example, well, for example, we could take the diagram we already saw. Ascend goes to point, and replace it with another one which is homotypic equivalent, but such that both arrows are cofibrations. We know that inclusions of CW subcomplexes are cofibrations. Okay, so we conclude that the homotypic colimit of this diagram is the same as the regular colimit of the bottom row, which is the sphere Sn plus 1. And for limits, the story is similar. Do we want to spell it out? Yes, no? Okay, so we claim that there is a model structure on C to the D, which is not the same as, well, not in general the same one as the one we started with in the first case. Such that C so I have C and C to the D. Now, this time the functor delta is a left adjoint, so it has a right adjoint, which is lim, and the claim is the junction becomes equivalent junction. So we have an adjunction of the derived functors. Did I mix up the arrows? No. So we have a similar junction of the of the functors between the homotopy categories and too many arrows going in the same direction. Okay, so we have a similar junction for these functors, and the one on top, the left. No, sorry, it's the other way around. Sorry, the one on top is the delta, and the one at the bottom is the homotopy limit. So the if I have an arbitrary diagram x, y, z, then the homotopy limit of this diagram is the same as the limit of the diagram with the primes. If y prime is fibrant or fibrant, and both arrows are fibrations. Well, for example, if yes. Сава, в чем вопрос? Совершенно непонятно. Сейчас. Почему можем? А мы не заменяем нигде. Значит, два разных утверждения. Одно про предел, другое про копредела.
Ну да, вот слева написано. Мы заменяем геометрический копредел на просто копредел. Обычно, чтобы взять какой-то...
Сава, это computational recipe. Значит, рецепт вычисления. Значит, давайте еще раз посмотрим. Вот у меня есть такая диаграмма, я хочу вычислить гомотопический копредел. Я ее заменяю на лучшую диаграмму, и у нее беру уже копредел. Не гомотопический копредел, а просто копредел. Значит, результат такой, что копредел нижней диаграммы представляет в гомотопической категории гомотопический копредел верхней строчки. Гомотопический копредел, он существует только в гомотопической категории, но его представитель — это копредел, обычный копредел, нижней строчки.
Я просто спрашиваю, почему это корректно. В том смысле, что вот обычно, чтобы взять какой-то слой, мы берем там обратный образ с пространственных путей. Ой, ну да, с пространственных путей.
Сейчас, слой чего? Здесь копределы.
Ну ладно, тогда берем, что чтобы взять такой слой, берем там с конусом. Да?
Правильно.
Почему он не работает? Я просто пытаюсь отнести определение, которое я знаю, с определением, которое здесь написано.
Да, здесь вот то, что начинается суд, это не определение, это вычислительный рецепт.
Хорошо.
Значит, возникает вопрос, а почему вычислительный рецепт дает корректный ответ? Значит, про это мы сейчас ничего говорить не будем. So, what I've described here is a recipe. It's not the same as a proof that the recipe works. And actually, maybe the well, I don't think it's. No, well, anyway, I don't think it's very complicated, but we'll nevertheless not mention, not go into detail on why exactly this recipe works. But once we've seen transfer of model structures, then it would make hopefully more sense. Anyway, example. Again, we take C top and the Hamilton limit of this diagram is the same as the homotopy fiber of this map, or in other words, the cell fiber. Does this make sense? Okay, so now what does it mean that APL what does it mean that APL preserves homotopy pullbacks? Or, in general, let's instead of APL, let's consider just an arbitrary functor f from C to D, where C and D are model categories. Well, let's see. So, well, firstly, I take a diagram of the pullback type. Then I using the recipe I just mentioned, I replace it with a better diagram. In other words, I assume that y prime is fibrant and both arrows are fibrations. Then I apply the, let me call this diagram D. And the bottom one will be D prime. Well, I have I have my functor f. I apply it to d prime, and let's see what I have. I have, well, firstly f of d. Then I have f of d prime. And then I also have the okay, so if I have a diagram, then there is a map from so I have the limit and the homotopy limit. My claim is I have a map between these. In which direction does the map go? Well, as it is clear from this diagram, the map goes from upstairs to downstairs. So the genuine limit goes to the homotopy limit. Okay, so and for co-limits is the other way around. How co-limit maps into the co-limit. Okay, so and well, let's assume, although this needs to be checked, that the map from the limit to the homotopy limit is functorial. So the phrase that f preserves homotopy co-limits homotopy limits, homotopy homotopy pullbacks. In fact, here I'm only talking about limits and co-limits of a very particular type. In most cases, we have more or less arbitrary small limits and co-limits, but the general axioms of a model category do not suffice to prove that those exist. One needs some extra structure. Let's have a look at this diagram. From what we know already, if we want to calculate the value of the derived functor, we need to first resolve a diagram by a fibrine diagram, and then take the apply the functor, take the homotopy co-limit. So this is the correct answer. If we want to calculate the homotopy co-limit applied to the diagram. On the other hand, this is the homotopy co-limit of the of f applied to the diagram. So f preserves homotopy pullbacks if which of the arrows is a weak equivalence. Yes, the right vertical. This arrow is a weak equivalence. Okay, so now we sort of understand which arrow we need to compute if we want to calculate, if we want to see whether or not a functor preserves homotopy pullbacks. Okay, are there any questions? Now, the Eilenberg-Moore theorem is very useful. Actually, what's your name? Tichi? Jiping. Okay, so Jiping in a couple of weeks will talk about a very particular case of the Eilenberg-Moore theorem, and this case allows one to model vibrations. Meaning, if we have a self vibration and we have a base and a fiber and so on, we are able to construct a Sullivan model for the total space, starting from Sullivan models for the base and the fiber. Okay, which is basically something that generalizes the CR spectral sequence. A spectral sequence is a partial answer. It tells us something, but not everything. The model tells us everything. Anyway, so now we want to apply the Eilenberg-Moore theorem to show that the derived no, is it co-unit? No, I think it's a unit. Okay, so we have let's consider rational abelian spaces. Well, let's consider the homotopy category of those. And we have CDJs. We have APO. And we have the APL functor. We have the corresponding derived functor, and we have the functor which is the derived functor of the geometric realization functor, which we also constructed last time. Very well. Now, if we have a pair of adjoint functors, then we have the unit and the co-unit. Does anyone remember which way they go? Oh, there's one thing which is wrong in this formula. Can anyone tell me which one? There's one thing that doesn't work. Yes, I forgot to put an up here. Okay, so we have a left adjoint and a right adjoint. Very well. What do we do with those? Well, we need the unit and the co-unit. Which way do they go? So I have, let's say, C. I have D. I have a right adjoint and a left adjoint. And now I want to remember which way do the unit and the co-unit go. Can anyone help me? without Wikipedia. So, in which order? Okay, so right adjoint. Okay. So if I take first the right adjoint and then the left adjoint, then I get a functor from D to D. So do I have a map from the identity or to the identity? Okay. Does everyone agree? Or is it the other way around? Well, there's a simple way to check. D DLXY is C Y X R Y. Okay, so now let me take Y equal LX. Then I have LX, which has a very distinguished map, the identity map. So I get a map from the identity of C to no, the other way around, to R composed with L. And similarly, if I take X equal Y, I get the map from R composed with L to the identity of D. Okay, so we have this map, which is the co-unit, and the other one, first apply L, then R, E to C, and this is the unit. It's always it's hard to remember, but easy to check. Okay, so the map we want to calculate is the unit. I suppose I have a sufficiently nice space. I first go to city J's, and then I return to spaces. And what do I get? Well, I get a map, not spaces. Okay, I get a map from K to I get a map of simplicial sets from K to APL of K in brackets. Very well. And I want to show that this map is a homotypic equivalence if K is abelian and rational. By the way, what does it mean abelian? Does anyone remember? Say again? Yes, the action of pi 1 on every pi n is trivial, which for n equal 1 means that pi 1 is abelian itself. Very well. And if I have an abelian space, then what does rational mean? there are basically two equivalent conditions. Yes. Well, the first one is that every pi n is a rational vector space. Since pi 1 is a billion, it makes sense to ask whether or not it's a rational vector space. Or equivalently, the reduced integral homology, each reduced integral homology group is a rational vector space. Well, let's also say connected. Okay, so I want to prove this for each abelian space. Now, each abelian space has actually the K is not a space; it's a simplicial set. But Postnikov towers work in the same way for simplicial sets and for spaces. And in a minute, we'll see that in the simplicial case, there is a nice model for Eilenberg-MacLane spaces. But basically, the Postnikov tower we saw in the very beginning has a straightforward analog for simplicial sets. The only difference is, instead of self-vibration, I say count-vibration. Otherwise, there is no difference. And I don't say what a count-vibration is, because it doesn't really matter. Very well. So the well, now I want to use. You see, I have the right adjoint which preserves limits, but the left adjoint does not have to. This is where the Eilenberg-Moore theorem comes in. So the Eilenberg-Moore theorem implies the following. So suppose I have suppose I have a fibration of simplicial sets, then well, then I have I have this this diagram, which is good for calculating homotopy homotopy pullbacks. I I apply APL, but APL is contravariant. We will we will need this in a minute. So APL is contravariant. So if I want to calculate the homotopy limit of this diagram in CDJ op, I need just to calculate the homotopy co-limit in CDJ, and then this will be the answer. Okay, so I take Sullivan models for everything. And moreover, I assume that at least one of the arrows is a cofibration, which means one of the. In fact, I've just said two, but one suffices. If one of the arrows is a cofibration, and these two are cofibrant, but the arrow is not necessarily a cofibration, then the answer is still correct. Anyhow, we take a sufficiently nice resolution of this diagram. And then I apply the geometric realization functor. So I take everything and apply the geometric realization functor, and the result is APLK in brackets PL in brackets PL T in brackets del F in brackets. Okay, so I have this, and then I have a map from this to from this diagram to the square brackets applied to the limit of the lambdas. Actually, let me write it like this. Oh, the co-limit. Sorry, the co-limit of the lambdas, which which calculates the right answer, and I have the original diagram. So this diagram maps to this diagram, maps to this diagram. And the well, let's forget about the diagram on the right. No, let's forget about the diagram in the middle. Let's look at the diagram on the right. So my claim is that this is, this is a vibration diagram. This is what we assume. Now, this may not be a vibration diagram, but this one is. The one on the right. Why? Can anyone tell me this? I mean a diagram such that the homotopy limit of this, the homotopy limit of this part is the remaining the remaining element of the diagram. If we have an arbitrary commutative diagram, we also have a map from the limit to the homotopy limit. And if we just have a commutative diagram, then F maps into the limit. So for an arbitrary diagram like this, we have a map, maybe not Cartesian at all. We have a map from F to the homotopy limit. But this map may or may not be a weak equivalence. If the map is a weak equivalence, we say that the diagram is a vibration diagram. No. Well, let's see. So this functor is the geometric realization functor. Is a right adjoint in equivalent adjunction. So it must preserve vibrations and fibrant objects. So if I have a but in our case, everything gets interchanged because both functors are contravariant. So if we have a co-fibration diagram, lambda 1, lambda 2, lambda 3 co-limit, then after applying the geometric realization functor, we get a fibration diagram. Is this trick clear, and does everyone agree with it? Okay, now if we have two vibration diagrams of simplicial sets, then we're in business. We can deduce things about if we have a base, a fiber, and a total space. We can always try to deduce things about one of them using some other things about the other two. Well, let's be more, a little bit more concrete. Suppose I have a commutative diagram of Serre vibrations. It works the same way for simplicial sets, but let's focus on Serre vibrations. Now I want to make a statement of the form 2 out of 3. Can anyone help me? Well, basically, I want what I want is if 2 out of the 3 vertical arrows are equivalences, so is the third one. But in order for this to work, I need to make some assumptions. Or shall we say, I can prove this using some extra assumptions. well, yes. One way would be to use the 5 lemma. And Whitehead's theorem. But still, there are, if we have a long exact sequence of homotopy groups, there are problems at the end. Let's see how one can avoid those problems. Well, in any case, we will only need this for abelian spaces. Let's say let's assume all spaces let's assume that all spaces are connected to an abelian. In particular, each of the long exact sequences terminates as follows: pi 1 of f, pi 1 of e, pi 1 of b, full stop, meaning 0. There are no tricky problems related to the fact that pi 1 may not be abelian, or pi 0 may not be a group. Let's just ignore those problems completely. Okay, does everyone agree with this argument? Very well. As a result, let me erase this. Let me erase this. So, let's assume that the unit the derived unit is an isomorphism for k pi 1s, k pi n's, not necessarily k pi 1s, where pi is a Q vector space. And let's let's see what happens, by the way, if we if we take a point, my claim is the APL if we take APL, apply it to a point, more precisely to the simplicial point, then take the geometric realization, we get our point back. Can anyone tell me why? Without calculating anything. Even better. The right adjoint preserves co-vibrations, vibrations and acyclic vibrations. And the left adjoint preserves co-vibrations and acyclic co-vibrations. Okay, so we does this allow us to conclude this without explicitly computing anything? Let's see. Well, sort of. So APL itself, let's assume that this, by the Ram's theorem, by the Ram's theorem, the APL of a point has the homology of a point and the cohomology of a point. Very well. Now we need to take the we take a co-fibrant resolution. Actually, in this particular case, well, Q is co-fibrant as a CDJ. Why? Because it's the initial object. And the map from Q to APL will be a co-fibrant resolution. Okay, now the right adjoint, after we remember that the right adjoint is in fact something which needs to be taken in the opposite category, the right adjoint will preserve an equivalence. So if I apply the geometric realization, I get the geometric realization APL of PT. To the geometric realization of Q. And the geometric realization of Q is a point, which is not very hard to check starting from the definition. Very well. so the most important thing is that this is a cofibration, and it's an acyclic cofibration. So when we apply the geometric realization functor, we get another acyclic fibration. Well, it doesn't matter that it's a fibration. What matters is it's acyclic. Okay, so to conclude, if we somehow prove the theorem for k pi n, if we prove that the unit has an isomorphism for k pi n's, then it's an isomorphism for an arbitrary rational abelian space using the Postnikov tower. And then, obviously, the question is very well, but how to prove this for k pi n's? And on this note, I would like to stop, and then let's have a break, and during the break, let's think whether or not we want to know anything about k pi n's. Значит, итого, я предлагаю сейчас сделать перерыв и подумать, хотим ли мы послушать про КПН. Если мы хотим, то я про них расскажу, и тогда, наверное, вы начнете в следующий раз. Потому что, так или иначе, у нас, Миша, я правильно понимаю, что вы уходите все равно на независимо сегодня? Да, значит, у нас будет тогда времени не больше часа, и это явно недостаточно. Хорошо, тогда, значит, у меня такое предложение. Давайте мы сегодня там закончим это, там чуть, может быть, поговорим про что-то похожее, а потом, значит, в следующий раз вы уже, значит, с самого начала начнете ваш рассказ. Okay, so plan A for today is to finish this and talk a little about similar things, and then Alexei will start his presentation next week, and Mikhail, same applies. Okay, are there any questions? Да хоть что-нибудь. Ну, значит, смотрите, у нас возник конкретный вопрос. Assume something, значит, то есть предположим, что что-то верно для КПН. Возникает вопрос, оно вообще верно, может, оно неверно? И вот, значит, я хочу про это сказать пару слов. Значит, действительно есть рецепт, значит, подсчета КПНов в симплициальном мире. И мы про него чуть-чуть поговорим. Okay, are there any more questions? Very well, then let's have a 20 minutes break, and then we'll continue. Ну, кто мы? Ну, я, наверное, смогу все выслушать, но возникает вопрос, кто сможет и захочет ли кто-нибудь слушать другие доклады. Еще остается вариант доклада по субботам в Zoom. В каком-то смысле это немножко другой жанр, но почему бы нет. Например, от докладов в Zoom остаются записки, которые можно смотреть, сохранять, от вот этих докладов ничего такого не остается. Так или иначе, может быть, еще не все захотят делать доклады, такое тоже не исключено. Так, давайте мы все сотрем. Так, Миша, Алексей, удалось ли вам разобраться с темами, которые вы будете рассказывать?
Минимально, да, я следующую неделю, я вроде чуть больше пойму,
Хорошо, то есть мы уже чуть-чуть знаем про модельные категории, но чуть-чуть. Нельзя сказать, что мы про них знаем очень много. Нам бы хотелось узнать, почему эквивалентны несколько вариантов определения квилин сопряжения. Вот я говорил, что правый сопряженный сохраняет фибрацию, то же самое, что левый сопряженный сохраняет кофибрацию. А почему? Или в смысле фибрация от заклеечной фибрации, кофибрация от заклеечной кофибрации. Но в любом случае возникает вопрос, а почему? И этих вариантов там несколько, но хотелось бы понять связь между двумя или тремя из них. Дальше возникают функторы на производных категориях, а почему они сопряжены? Дальше сама теорема о том, что при каких-то условиях эти функторы эквивалентность, она довольно-таки очевидна. Мы просто говорим, что функторы задают эквивалентность, это тогда, когда единица к единице изоморфизм. Прекрасно. Мы это, в общем, более-менее так, об этом догадывались. Здесь хочется понять, а почему действительно существуют функторы производные из одной гомотопической в другую, наоборот, и почему они сопряжены. Так, Миша, удалось ли вам разобраться?
Тоже
к следующей неделе лучше. Хорошо. Тогда, соответственно, если вы в следующий раз тоже будете уходить в 7, тогда, просьба организовать доклад так, чтобы там... В общем, значит, идея в том, чтобы продумать заранее план и, значит, ну, не фантазировать у доски, потому что, значит, не потому что это плохо, это наоборот хорошо, но времени мало. Okay, so let's state the proposition will be proving. Actually, I've just realized that I only know how to prove this for finite dimensional vector spaces. So let's assume that. Let's recall how to pass from k pi n to k pi n plus 1. Okay. So suppose I have this diagram, and I want to make it a vibration diagram. What do I need to put here? N minus 1, yes. And by the way, if you look at this diagram without the upper left corner, then the limit is nonsensical, but the homotopy limit is k pi n minus 1. Okay, so well, from the theorem we stated last, not last time, half an hour ago. It suffices to prove the proposition for n equal 1, and then we use the same principle as before. Only before we use the fiber plus base implies the total space. And now we want to use total space plus fiber implies the base. And all spaces are abelian, which is more or less clear and connected. Okay. Now, how to handle the case n equal 1. Again, we use the composition is the identity. Now let's return to the Eilenberg-MacLane space, KQ1. So we have a simplicial KQ1, and we need to calculate this map. More precisely, we need to show that this map is a homotype equivalence. If we somehow know that the space on the right is abelian, then actually, let me write a lambda here, where lambda is a cofibrant model, because let's remember that in is a quasi-isomorphism. And this is something, something which is easier than what we started with, because lambda is a very simple algebra. Note that here we don't need to take any replacements. Lambda is already cofibrant, so the geometric realization of it is already good for calculating, so lambda is already good for calculating the right adjoint, which is the geometric realization. Okay, and then in simplicial sets, all objects are cofibrant. So I just take APL of the geometric realization by junction it maps to lambda, and this is what I need to check. Does any of it make any sense? So, in other words, this general nonsense allows one to replace calculating the unit, which is sort of complicated, with calculating the co-unit, which is easier. So, summarizing. The proposition for 1 it suffices to show that lambda lambda of x in degree 1, the geometric realization lambda is abelian, and the co-unit not the unit, the co-unit APL of lambda goes to lambda is a quasi-isomorphism. This is something that can be done by hand. So, modulo this, we have shown that for all, well, at least for all spaces which are abelian and are rational of finite type, the junction unit is an isomorphism. Of finite type, meaning all homotopy groups are not just Q vector spaces, but finite dimensional vector spaces. Okay. Now, what does this tell the full subcategory of such spaces in the homotopy category of all spaces? Well, let's remember something we already mentioned and used. If we have an adjunction, then we have an equivalence. Of the full category of C, such that the unit is an isomorphism, and the full category of D such that the co-unit is an isomorphism. Okay, what does this tell us? And this is the last thing we will see today. For example, if you take if you take a wedge of two circles, the minimal model will just explode in degree 1. Unfortunately, combining the two results, we get an equivalence between the full subcategory of spaces which are abelian of finite type and simply connected and connected, and the category of CDGAs which are again connected and simply connected, and are of finite type. By finite type, we mean the homology is of finite type.